All right. I hope everything's going well. I'm doing a screencast on this DDD that you guys need to be working on. And this one is the one that has double and single slit interference at the same time, which all double slit experiments actually have. But sometimes we ignore it because the size of the slit is so small compared to the distance between the two slits that we ignore the single slit envelope. But here's a problem where the single slit envelope is super important. So let's take a look at what we got here. So this graph here is showing in the red the intensity of light, and you see how it spikes up and down a lot, and that's shown here. I'm trying to show, and this was from an earlier screencast, how it goes bright, dark, bright, dark, bright, dark as it goes along, and then here's this big dark spot that's caused by the single slit envelope. So what they've done here is they've graphed how bright it is, and it's the red graph that's the actual graph. The green line here is just trying to show you the single slit overlay envelope that cuts off the double slit pattern, as you can see here. And the units here are important. This is radians, and that's going to help us understand. Please notice there's a lot more red spikes here than in this picture. This is just for reference, giving you the idea of what this graph's actually about. Somebody get rid of that because actually it's wrong. So here we want to realize that the angle from 0 over to 0.1, that of 0.1 radians there, is the theta that we would use in this equation that we use when we have single slit diffraction right here. Instead, the angular distance between each of these tiny little, the red, spikes here, that's the double slit pattern, the interference pattern, that's going to be given by this. So on our diffraction, we have 0.1, but they haven't given us a good way to see what the interference angle is. But let's just count how many there are. So if I start in the middle and I go over, there's 1, 2, you just got to be careful here, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 of them. So that's very convenient, and why I wrote this question, so that our 0.1 radians for the single slit, and there's 10 of these little guys in here, so that means that their angular distance from peak to peak on these red spikes is going to be 0.01 radians. Okay, so that's what we would use for theta here, 0.01, and then what we would use for theta here, we would use 0.1. Okay, and we have both of these equations ready to go. The first question, find the distance between the two slits. So between the two slits, that's what we're calling D. That's going to be the smaller of the two, right? So that's this guy. So that's 0.01. That means we're going to use this. Think about the 0.01 radians and go ahead and solve this. Now, if we're thinking about just this one right here, calling that 0.01, then obviously N is 1. Lambda is given of 680. D is what we're trying to find, and then sine theta, when it's in radians, 0.01, sine of 0.01 ends up being just 0.01. So we end up taking 680 on this side divided by 0.01. So that's just basically times 100. So we would take this number here multiplied by 100 for the answer to A. For B, if the screen is 2.5 meters away, what is the distance between the red dots that are observed in centimeters? So you could do this with the old SL equation where you had S and capital D and all of that, or you could just realize that on the screen, you're going to have the distance from the screen, which we usually call capital D, and then the distance between the fringes that you're observing on the screen. That's what this is. This is showing the screen and the little bright spots on the screen. So the distance between those we usually call S. And so tan theta is going to be this S distance here divided by capital D, how far away it is. But again, tan theta at small angles is still theta. So you can still use 0.01 as tan theta and then just solve that real easily. I guess I can show the math there because I have it down here. Yeah, here we go. So here was A, we divided by 0.01, so we got a lot of nanometers here. I think it's good to switch units there and go to 68 micrometers. For B, we're saying tan theta is 0.01, so that means S is 0.01 times D, and I guess D was given, 2.5 meters away. So that's nice. So you just take that, and we get 0.025 meters, which is about 25 millimeters, or 2.5 centimeters. Okay, C. What was C? C. What is the width of each slit? So that's going to be this whole big guy here, because that is the width of each slit is given by B. And remember that B is, much smaller than D in these, which makes sense. So that D gives us smaller radians by 10 times. And that means that B has to be 10 times smaller than D. It's that easy, actually. So the ratio of B to D is also the ratio of the fringes, which is what this is attempting to show us. So by doing that, we just have to divide by 10, and we get 6.8 micrometers. So the math here is super easy if you've actually understood the idea of that ratio of the theta comparison back to here. This theta compared to the theta of just one peak is the same ratio, that angular ratio for small angles is going to be the same as the ratio of D to B. Obviously the other way around, inverted obviously, because obviously B is smaller than D, but the angle related to B is always going to be bigger. The single slit envelope obviously is bigger than the double slit little fringes. And I say obvious, but that's obvious if you had seen the other screencast. So if that wasn't obvious to you, you might watch that other screencast again, which is linked in the problems of the day. So I hope that helped a little bit, and I hope things are going well for you in this this crazy time, and keep studying and keep doing your best, and hope to see you soon. All right.